China has just revealed a supersonic jet engine that's rewriting the rules of flight. Built by the Institute of Engineering Thermophysics, this adaptive cycle engine can literally change how it breathes mid-air, boosting thrust by nearly 50% while cutting fuel use by a third. And here's the shocker. It's designed to perform efficiently all the way up to Mach 4. China's latest technological leap comes from the Institute of Engineering Thermophysics, where researchers claim to have tested a revolutionary, adaptive cycle engine capable of operating smoothly from takeoff speeds to an incredible Mach 4. This engine represents one of the most ambitious advancements in jet propulsion, a design that adapts its airflow, thrust output, and fuel cycles in real time to maintain peak performance under drastically changing flight conditions. Traditional jet engines are limited by their design focus. Turbofans are optimized for efficiency and quieter operation at subsonic speeds, while turbojets are designed for high-speed thrust but consume far more fuel. China's adaptive cycle engine, ACE, bridges these two extremes. It does this by incorporating three separate airflow paths, a design that sets it apart even from advanced Western prototypes like the US GE XA-100 and Pratt and Whitney XA-101, both of which employ dual bypass configurations. This third airflow stream serves multiple purposes. It channels cooler air around the core, significantly improving thermal management, reducing infrared emissions, and enhancing stealth performance by lowering the exhaust heat signature. The same airflow can be mixed and burned for an additional thrust boost when required, a process known as bypass combustion. This gives the engine a near-hybrid quality, acting as a turbofan during takeoff and efficient cruising, and transforming into a turbojet capable of near-hypersonic speeds. Reports suggest the Chinese ACE achieved 27 to 47% more thrust and cut fuel consumption by up to 30 to 37% compared to current high-performance engines of similar class. If accurate, these results would put it ahead of any known operational jet propulsion system worldwide. The Mach 4 performance mark, approximately 4 times the speed of sound, represents a limit previously unattainable for turbine-based systems, pushing the engine into an area traditionally reserved for ramjets or scramjets. Beyond raw numbers, the adaptive behavior of this engine also improves inlet efficiency, pressure recovery, and drag reduction at high speeds. By dynamically adjusting airflow distribution between its three streams, it maintains stable combustion and engine temperature across extreme altitudes. If proven accurate, this adaptive cycle engine could mark a defining moment in the evolution of aerospace propulsion. The leap from conventional dual bypass systems to a three-stream adaptive design is not a small one. It signifies a rethinking of how engines handle energy, temperature, and airflow. For aircraft designers, it removes long-standing compromises between speed and endurance, a balancing act that has limited jet performance for decades. The potential implications are enormous. An aircraft powered by this engine could achieve higher thrust-to-weight ratios, making it capable of faster climbs and longer ranges with less fuel. This translates into greater operational flexibility for future aviation, both for commercial and advanced research applications. For example, the same aircraft could take off efficiently from shorter runways, cruise economically across continents, and still have the power to reach near hypersonic speeds for emergency or experimental purposes. The third airflow stream also allows for active cooling, one of the most difficult challenges in high-speed flight. Excess heat from the aircraft's skin, electronic systems, and radar-absorbing materials can be absorbed and redirected through this cooler airstream, enhancing system longevity and reliability. This means the engine can operate in extreme thermal conditions without overheating, something conventional engines struggle with at sustained high speeds. In addition to performance gains, there are also potential environmental and economic benefits. A one-third reduction in fuel consumption means lower emissions and longer operational life for the engine itself. In a world increasingly focused on sustainability, efficiency breakthroughs like this could make high-speed flight more environmentally viable in the long term. While the United States GE XA-100 and Pratt and Whitney XA-101 adaptive engines also represent cutting-edge designs, they are generally expected to function effectively up to around Mach 2.5. The Chinese prototype's claim of Mach 4 efficiency goes beyond that limit, moving into a domain that could merge with future combined-cycle engines capable of transitioning between jet and rocket propulsion. If China can integrate this ACE design into real aircraft, potentially future iterations of its advanced jets, or even experimental hypersonic demonstrators, it would not only enhance performance, but also mark a symbolic step toward closing the technological gap with the world's leading propulsion systems. As exciting as these claims sound, it's important to separate tested data from theoretical projections. The announcement of the new adaptive cycle engine reportedly came during a domestic Chinese engineering conference, rather than through international peer-reviewed publications. This suggests that while the underlying thermodynamic principles are credible, the performance metrics, especially the Mach 4 claim, may refer to simulated airflow tests rather than actual flight data. Ground-based and altitude simulation tests can replicate airflows and pressures experienced at Mach 4, but they do not necessarily prove full engine operation under those conditions in a moving aircraft. Sustaining combustion, maintaining pressure balance, and ensuring turbine integrity at such extreme velocities remains an enormous challenge. Even advanced cooling materials, like ceramic matrix composites and superalloys, begin to reach their limits under prolonged thermal stress beyond Mach 3. Another key point is scalability. Laboratory prototypes often use simplified or scaled-down systems optimized for demonstration. Translating these designs into full-size, operational engines introduces challenges like material fatigue, weight distribution, vibration resistance, and maintenance feasibility. Each of these factors must be solved before an engine can transition from prototype to production. That being said, the concept itself is very plausible and aligns with the direction of global propulsion research. Adaptive airflow systems and three-stream mixing have been active areas of study in the United States and Europe for over a decade. What makes the Chinese announcement significant is the reported progress toward integrating these systems into a functioning prototype that reportedly achieved measurable thrust improvements. It's also important to acknowledge how announcements like this often serve as technological signaling, demonstrations meant to showcase national innovation capability rather than confirm operational readiness. Even if the engine is still in early testing, it indicates China's growing emphasis on developing fully indigenous propulsion technology. In conclusion, whether or not the engine has yet reached sustained Mach 4 operation, its existence points to a clear future trend, one where engines are no longer static machines, but intelligent systems that adapt dynamically to every phase of flight. China's new adaptive cycle jet engine could mark the beginning of a new era in flight, one where engines can think, adapt, and perform seamlessly across every speed. If the reported 47% thrust boost and 30% fuel efficiency gains hold true, this would represent one of the most significant propulsion breakthroughs in modern aviation. Whether it's powering next-generation aircraft or paving the way for efficient supersonic travel, this shape-shifting engine is proof that the race for smarter, cleaner, and faster flight is accelerating, and the future of aerospace innovation just got a major push forward. If you enjoyed this video, don't forget to like, share, and subscribe for more updates on space exploration and scientific discoveries, and don't forget to leave a comment below. Also, you can visit our website, SpaceEyeNews.com. Thank you for watching, and see you next time.